Okay, hi everyone. You'll notice, like a true college student, rather than take a shower this morning, I just put a baseball hat on. Let's see. It's not so bad, but anyways, in the last video, I introduced this concept, chemical potential. This is the formal mathematical definition, and the idea is that the chemical potential describes a kind of potential energy which is associated with the composition of a system. Systems can lower their energy if they change their composition sometimes. And what's most relevant about this is it allows us to define, it provides us a way to define equilibrium. Specifically, we know that at equilibrium, the chemical potential of a substance is the same throughout the entire system, regardless of how many phases are present. That's the most important thing. I left with this sort of teaser, which is to say that we seldom calculate the chemical potential directly, but we use it to connect other variables. And today I'm going to give you probably the most important example of that, which is called the Clausius Clapeyron equation, right, described in Atkins 4b. So let's get into it. We'll start here. Let's imagine some state of a system in which two phases are present in equilibrium. To try and give you a specific example, let's imagine a liquid-gas equilibrium. The idea is, given some P1, T1 point on a phase boundary. So if I have both liquid and gas present, I know that I'm at a phase boundary. And if I have both P1 and T1 present, if I do this, I call this P1 and T1, you could imagine that I might want to calculate some other combination, which I would call P2, T2. Right? So how do I do that? How do I calculate some other set of equilibrium conditions along this phase boundary? In everyday language, this has a little more common meaning. And what you're basically saying here is that you want to calculate the vapor pressure at different temperatures. Remember, one way we can think about this line is it's simply the vapor pressure at different temperatures. There's a complement to that, which is an equivalent statement, which is to say that I want to calculate the boiling point at different pressures. So remember from organic, if you put your system in a rotovap and draw vacuum on it, you decrease the boiling point. Right? So I could say I want to calculate the boiling point at different pressures. In order to do any of this, what you might recognize is that you need the slope of the line, right? That's what we're looking at. These changes are related to the slope of the line. Pressure on the y-axis, temperature on the x-axis. So what we really need here is dP dt. Okay. I'll walk you all the way through this. We're going to do a very general derivation. So we're going to consider some general equilibrium, which I'm calling alpha to beta. It could be anything. At equilibrium, I know that the chemical potential of alpha is equal to the chemical potential of beta. Or in differential form, d mu A is equal to d mu B. I can go back and look at previous slides, and the chemical potential for a pure substance is the molar Gibbs energy. So d mu A is the molar Gibbs energy. And I go back to that natural equation and I get an expression which looks like this. So it's the molar entropy dt plus the molar volume of alpha dP. I get an expression for alpha phase. I get an expression for the beta phase. Because these are equal at equilibrium, I can set them equal to one another. I'm then going to group all of my dP terms on the right-hand side and my dt terms on the left-hand side. So that brings this alpha over here, and it brings this beta over here. Now I simply use this expression or equation to derive an expression for dp dt. That is, it is delta S molar of the transition divided by delta V molar of the transition. This is a named equation. It's called the Clapeyron equation. One of the nice things about this is that it will always work. We've made basically no assumptions at this point. So this equation will always work, but because it's so general, it isn't always the most helpful. And so what we're going to do now is consider some phase transition and make some reasonable approximations. Here's the first one. Let's talk about a vaporization, liquid to a gas. So starting at the Clapeyron equation, I need some expressions for delta S and delta V. Well, recall that for a phase transition, this is the definition of the change in entropy, delta H divided by T. In the denominator, I needed delta V molar. And in this case, this would be V molar of the gas minus V molar of the liquid. And what you might recognize is that the molar volume of the gas is much, much larger than the molar volume of a liquid. The liquid is much more dense, the gas is much less dense. And so I make an approximation to say that this difference between the molar volume of gas and liquid is approximately equal to the molar volume of the gas. We go through and make a second approximation, which is to say that I'm going to assume the gas behaves ideally. The molar volume of the gas is RT divided by P. You start to put this all together, dp dt, delta S over delta V. You start to plug in your expressions. I now get something which looks like I can integrate it. Right? Over here, I have a dp variable, so I'm going to bring all my p's over the left-hand side. And on the right-hand side, I'm going to get a dt variable. So if I group those, I get an expression that looks like this. I can now integrate it. So I integrate both sides. And I'm going to make one more assumption, which is going to make my life easy, which is basically that delta H VAP, the enthalpy of vaporization, is constant. R is a constant, it's the ideal gas constant. But if I assume that this is constant, I can pull it out front of the integral. I throw some limits on it, P1 to P2 and T1 to T2. And I end up with this important equation. It's called the Clausius Clapeyron equation. Natural log P2 over P1 equals negative delta H VAP over R times quantity 1 over T1 minus 1 over T2. If you're a note taker, put this in your notes and circle it. There are two important uses of the Clausius Clapeyron equation. So here's the first idea. If I know delta H VAP, if I know what this quantity is, I can calculate the vapor pressure at some other temperature, assuming I know one set of equilibrium conditions. So if delta H VAP is known, oh, my battery's low. Let's see if I can get through this. Delta H VAP is known, and I know P1 and P2. P1 and T1, sorry, if delta H VAP is known, I know P1 and T1, I can calculate P2 at some temperature. In order for this to work, you have to know one set of data points, P1 and T1. And it turns out there's one which is almost always known. Right? The most common set of known equilibrium conditions is, anyone? I see a hand in the back. It's the normal boiling point. Right? If you know the normal boiling point, the temperature at which it boils when atmospheric pressure is 1 atm, you have one set of conditions. That's one use of the Clausius Clapeyron equation. Here's the second. if multiple sets of equilibrium conditions are known, that is, I know P1, T1, P2, T2, P3, T3. I know the vapor pressure at a series of different temperatures. I can calculate delta H VAP. So this is the complement to that previous usage. And in one of the early videos, I showed you this slide. We were talking about gases, and when we were analyzing gases, we plotted P versus 1 over V, so we got a straight line plot. This is my old postdoctoral advisor who said all science can be reduced to a straight line plot where we interpret the slope or intercept. That was the idea. Well, if I had some PT data, what would we plot to determine delta H? There are different ways that you might think about this. I'm not going to go into it in great detail. But if I start at this expression and evaluate the indefinite interval, you get something which looks like this. Natural log P, bunch of constants, 1 over T plus some offset. And this, I hope, makes it obvious. What you would plot is the natural log of P versus 1 over T. And what we would expect to get is a straight line whose slope is equal to negative delta H VAP divided by R. I'm not going to go into it here, but it will turn out that this intercept is related to delta S of the transition. And it's actually the standard delta S. But we can talk about that another time. All right. You can go through a similar set of analysis for other types of transitions. Here's what it looks like for fusion. Fusion is the thermodynamic term for melting, a solid to liquid transition. I'm not going to go through the derivation. You can do it if you're bored. It's not so bad. The formal expression looks like this. It's very easy to evaluate with calculators, but back in the day, in the olden days, in the 1800s, when they didn't have calculators, they used a series of approximations to make this expression look linear. And so this is an equivalent expression, which is written slightly differently, and you'll see both forms of this equation. If you're a note taker, put that one in your notes and circle it, right? Solid to liquid transition. In summary, we've derived 3 equations here, or I guess we've talked about 3 equations. So the first was the Clapeyron equation. It's general, it works for all phase transitions, but because it's so general, it's not very useful. This is probably the most important one for vaporization, a liquid to gas transition. This is the Puckett-Herbeck equation for solid to liquid transitions. Stop here. I have one last thing I want to talk to you about in the discussion of phase transitions. That's in the next video. I will see you there. All right. I survived. My battery made it.